So, what in the world is a flowing robotic surface? Well, a flowing robotic surface combines a 20 by 20 array of 1D actuation and a smooth to the touch surface material to create 3D imagery that you can touch with your hands. It's optimized for use in scientific settings to show 3D renders of heat maps, topographical maps, data plots, and images. While our device can be used by anybody, our target audience is blind or visually impaired people who do not acquire the facilities to be able to see plots and important images. Through the user and robotic interface, a visually impaired user will be able to feel their data to create a mental image of what they're touching. This is where the term haptic imaging comes into play. This will allow the user to make scientific decisions based on their newfound knowledge of the data they have visualized. You never know what kind of discoveries can be made when science becomes fully inclusive.
Initial evaluation of the possible modes for linear actuation on a basis of cost, schedule, reliability, precision, and size resulted in a narrow win by fader motors. If you're not familiar with fader motors, they're essentially a sliding potentiometer to measure position, combined with a DC motor to provide movement. However, since servos came in as a close second, we decided to prototype both designs in parallel to validate our selection. Based on this validation, we progressed in an iterative manner, beginning with testing a single fader motor assembly to establish whether these motors would be capable of achieving our accuracy requirement. Success with a single point of actuation prompted the development of a 3x3 prototype. Although this prototype did not work fully as expected, the development and assembly process were instrumental learning experiences, enabling us to reconsider factors such as pin shape and device modularity. Additionally, software and electronics were tested successfully, validating the design before scaling for the final device. A modular design consisting of 20 banks of 20 motors enabling easy access was then implemented. As you may notice, some of the motors bounce more than others. This is due to differences in their internal resistance, which we have since corrected for through a mass calibration of all 400 motors used in the final device. Applying lessons learned, we have designed and built a fully functional flowing robotic surface with 400 individually actuated points.
One of the biggest engineering challenges inherent with this kind of project is how much everything needs to scale up. Each actuator needs several Arduino connections, generates heat and electromagnetic interference, and uses up power. Multiplying any of those issues by 400 pins can quickly make the project fall apart. Turning all of the manual wiring and circuitry into a custom printed circuit board makes much of the wiring more manageable and ensures secure connections between components. Switching from simple wires to shielded cables will isolate the modulating motor control signals from interfering with the readings from the potentiometers. Since each motor is rated for 10 volts with a maximum current of 800 milliamps, an array of 400 motors could use up to 3200 watts of power, which is more than we can reasonably assume a user could have access to. So we've implemented this control scheme where actuators will approach their targets incrementally and iteratively. This way, only a small portion of the actuators will need to be powered at any given time. Based on testing, we determined that this smaller panel of 20 motors is using a maximum of 180 milliamps of power at any given time, less than 2 watts. This should scale up to about 36 watts for the full device.
We created an Excel thermal model, inputted the estimated total motor power consumption, as well as the specs of the PC fan we were considering, and found the minimum number of fans needed to keep the temperature inside the housing below 50 degrees Celsius. The PC fans used in this system are lightweight, silent, and their rotations per minute can be tracked using the green wire. We can also control their rotations per minute by delivering a pulse width modulated signal via the blue wire.
On the software side, when a user inputs an image like this one, first it gets converted to black and white and scaled into the right aspect ratio for the display. Then we'll sample it at even intervals to get a final 20 by 20 pixel image. This image is then checked internally to make sure we can display it. If it's too jagged or discontinuous to be rendered on the display, we flatten it out a bit. That gives us a final set of points which are directly rendered on the display.
One method of data input is to save an image file to a USB drive and plug it straight into the Raspberry Pi. A second method of data input is to select and send a file to the robotic surface via the graphical user interface. It allows the user to select their own image file and simulates the 20 x 20 pixel version of the image. It includes audio readout of the image scale,
18, 2, 1,
simple zoom features, and a 3D simulation of the surface. When the user clicks the display button, the original image displayed on the left gets sent to a specified folder in the Raspberry Pi. The second tab of the GUI is a repository of use cases or sample image files that demonstrate the capabilities of our system. One such use case is the hydrogen orbitals. The GUI allows the user to change the quantum numbers and display different hydrogen orbitals in 3D, which could be useful in an educational setting.
Overall objectives for the surface was that it be flexible, lightweight, yet able to withstand the touch applied by a human hand. The original design for the surface encompassed a composite material where polycarbonate were to act as the base and silicone would be on the top. When manufacturing a sample version of the polycarbonate with tessellation cutouts, the sample proved to be sturdy enough to hold shape without deformation. However, when moving forward with the final 15 by 15 inch polycarbonate sheet, the piece failed when being cut. The team concluded that the reason for the polycarbonate failing was due to a thin thickness of 0.093 inches, and being that the polycarbonate has a relatively weak skeletal structure. And with the pressure of the water jet being too strong and the cuts too intricate, the water jet caused the material to fail. This was definitely a hurdle for the team, but we all came together to create an alternative version where we are now using an elastic material to be stretched over the wooden dowels. Future improvement and testing could involve creating a more rigid yet flexible surface out of a thicker material and perhaps a less intricate design.
A major component necessary for holding all of the electronics together, guiding the actuators and pins in the right positions, and providing a place to have a robotic surface is the housing for our design. The housing is meant to not only be the main structural component of our robot, but to also provide adequate ventilation for the 400 motors actuating inside. The design we developed uses great patterns on the side panels, hole cutouts to support PC fans for extra cooling, and large rectangular cutouts to place hinged doors for access to the internals. The main material used is 6061 aluminum to ensure rigidness when moving the assembled robot and during operation. What seems like a fairly simple design did come with a few drawbacks after the manufacturing stage, however. Ian, come here.
Yes.
We're gonna have to re-drill every single one of these holes. Look, none of these align. They're all off. Yes, the panels were cut 1/8 of an inch too large on all sides, leading to the holes and connecting tabs being non-concentric. Luckily, there's nothing a metal bit and a corded drill can't fix. Once new holes were measured and drilled, the panels were successfully joined to create the enclosure of our robot. However, the trials and tribulations didn't end with that. Through some sample testing with our wooden pins, we quickly realized the majority of the pins needed to be heavily sanded to fit the holes in the surface grid. So, 3 days of belt sanding later, the process was finally complete, and our robotic housing was finally assembled. Weighing in at 118 pounds, it will definitely need to be put on wheels. However, it meets the weight requirements for the entire system using weight analysis provided by SolidWorks.
Our MVP2 was a single panel of 20 motors. We tested motor accuracy by setting all 20 motors to the same target position and measured each motor lever position using a ruler. After 3 trials, we found that all 20 motors were positioned to within 0.3 centimeters of their target each time. This table shows that each motor in the 20 motor panel had a mean error of less than 0.3 centimeters, which satisfies our system requirements. Additionally, as of this moment, all system requirements have been satisfied and confirmed with our sponsor, except for one requirement which is in progress due to delays in PCB manufacturing.
I was able to give the team real-time feedback to help improve our prototype by design day. Additionally, I provided insight to the team as far as use cases, helped develop more efficient models for future scientists and students to use.